Hello everyone, my name is Professor Stephen Roman, and this is the first video in a video course entitled An Introduction to Discrete Mathematics. As with all of my video courses, there is a book that accompanies this course, and it's available on my website at www.sroman.com. The book for this course is a third edition of a textbook that I wrote in the mid-1980s. I can show you a picture of that book. This is my website. And here's the book. But I've made significant changes to the new edition. I've enhanced some of the discussions. I've included additional proofs. I've added some new material throughout the book. And in particular, I added a new chapter on more advanced topics in combinatorics. As you may know, if you've seen my YouTube channel, this isn't my first video course in mathematics. I've done 6 courses prior to this. Here they are. The first course I did was Category Theory, a very short course with just 6 lectures. The next course was a Transition to Advanced Mathematics. This was based on a class I taught several times at the University of California, Irvine. And the purpose of this course is to help students make the transition from the first 2 years of mathematics, which is primarily calculus with a little bit of linear algebra and a little bit of differential equations, to upper division mathematics, which is considerably more challenging. It's a fun course, I think, and it's accessible to people who are not math majors. I've had philosophy majors and physics majors in my classes, even a chemistry major or 2, biology. It's suitable for anyone who wants to get a sense of what mathematics is really like. The next 4 courses fall under the heading A Comprehensive Introduction to Abstract Algebra. And they are designed for advanced undergraduate students or beginning graduate students. The first course is linear algebra, followed by group theory, then ring theory, then field and Galois theory. So all total, if my arithmetic is correct, it's 166 videos. I learned the hard way by teaching during the pandemic that there are some advantages to video courses, especially in a highly technical subject such as mathematics. So I've been making these courses since I retired from teaching, which I did reluctantly. I would still like to be teaching, but I guess it was time to retire. One of the advantages is that I'm not constrained to either 30 lectures for a quarter course or 45 lectures for a semester course, which means I can do more lectures or fewer lectures, whatever seems appropriate for the subject. Also, the lengths of the lectures aren't constrained to 50 minutes. They can be shorter or even longer. I try not to make longer lectures. Every once in a while I do, but for the most part I try to keep them under 50 minutes. But of course, even if a lecture is longer, a video is an hour and a half, you don't have to watch the whole thing at one setting. Also, viewers of the lectures can pause and rewind a little bit if they're confused about something, or simply rewatch the entire video at a later date. That's not possible to do with a live lecture. Now, there are some disadvantages to video lectures as well, but much of those relate to the sort of bookkeeping aspects of a course, such as giving tests and homework. I guess students don't think of that as bookkeeping, but professors may do. The main disadvantage of a video course like this is the lack of direct connection with students. I was always very happy when students would come to my office and we could discuss things, and I always encouraged that. Also, there's a lack of direct feedback. Even though most students don't seem to want to raise their hand in class and say, I don't understand that, could you go over it again, which I would be glad to do. I can tell from the painful expressions or the glassy-eyed stares that I need to probably slow down a little bit or explain something in a little different way. Everybody learns, perceives differently, so sometimes more than one explanation of the same concept is very helpful. So none of that can be done in a video course. Now, in these lectures, I'm going to follow the book very closely. At times it may seem that I'm almost reading the text, but let me explain why I might do that. First, I'm not reading someone else's words. These are my words. And I've taken great pains to write in this book what I would otherwise say directly to students in a classroom. So it just feels natural to me that I would want to use the same words in these videos. Just because I wrote them down doesn't mean I shouldn't be able to use them. In fact, it seems to me that this is an advantage rather than a disadvantage. For example, when I buy an audio book on a topic of nonfiction like history or something with some real substance to it, as opposed to a novel, I also like to buy a copy of the written book so that I can listen and read at the same time. And I find that helpful to absorb the detailed material. So I hope maybe you will find it helpful as well, so you can listen to what I say and see the words in front of you at the same time. Now, of course, the mathematics, the symbols, the equations, and so on, and the graphs, the figures, those are important to be able to see as well as I discuss them. So hopefully you will be okay with this. I think in the 4 years I've been doing these courses and the hundreds of comments I've received, only 2 comments were something like, this isn't teaching, this is reading. So I think most people were okay with it, but you'll be the judge of that, of course. Okay, let's take a look at Chapter 1, Sets, Functions, and Proof Techniques. And we'll begin with some information on sets. Modern mathematics is founded on 2 fundamental concepts, sets and membership in sets. And before I get into the details on that, let's cover some notation. You probably know this, but I'll go over it quickly. The bracket notation is read the set containing. So for example, this reads A is the set containing 1, 5, A, and W. When the brackets are combined with a vertical bar, this didn't come out very well, did it? Then we read this as the set of all, and whatever comes before the bar, for which, or such that, and then you read whatever comes after the bar. So for example, B is the set of all x for which, or such that, x is greater than 5 or x is less than 2. by definition, sets are not allowed to have repeated elements. So an expression that looks like this is a mistake and should have been written like this. Whoops. I'll tell you what, I have this new piece of software, and I'll see if I can master it while I talk. So this is how the set should have been written, because repeated elements are not allowed. So this is really the set containing 1, 2, and 3. As to membership, to denote the fact that a set X is a member or element of a set Y, we write this. This is just a symbol. It looks a little bit like a Greek letter epsilon, but it's not. And if X is not a member of Y, we would write it this way. It's the same symbol with a line through it. So that's all the notation we need for now. Since the concepts of set and membership lie at the very foundations of modern mathematics, they can't be defined precisely, essentially because there are no more fundamental concepts that could be used to construct those definitions. In a sense, we have to start somewhere, and where modern mathematics starts is with these two concepts. So as a consequence of this, we really have no other choice but to rely on our intuition about the nature of sets and membership. And hopefully that intuition improves the more experience you have. But even very experienced mathematicians can make intuitive mistakes, and I'm going to talk about that in a few minutes. So intuition is far from perfect. It's faulty quite often, unfortunately. The formal study of sets belongs to a branch of mathematics called set theory. And this branch of mathematics was essentially founded by a single short article, I think it's 4.5 pages, written in 1874 by a mathematician named Georg Cantor, and here's his picture. This could arguably be thought of as the beginning of modern mathematics. And I'm going to spend some time later in the course discussing Cantor's seminal work on infinite sets, because I think all students of mathematics should have at least a passing acquaintance with that. It's an important subject. And I want to talk a little bit more now about the foundations of modern mathematics that took place, let's say, beginning in 1874 to somewhere around 1925. It'll be a short discussion, but it's quite interesting, I think. In the early days of the development of set theory, starting with Cantor's 1874 paper, it was generally felt that any collection that you could describe using the English language or some other language would constitute a set, a mathematical set. But in 1902, the mathematical community was rocked by a shock. That sounds kind of strong, but I think it's probably accurate. When a mathematician and philosopher named Bertrand Russell discovered a contradiction, and it led mathematicians to rethink their intuitive notion of what constitutes a set. In short, the mathematicians at that time were a bit too liberal about what they thought would be a set. And I can give you a lay version, a common version of what became known as Russell's paradox. And it goes like this. And after this version, I'll give you a little bit more mathematical version. Philip is a barber who lives in a small town. Philip has a strict rule, which he always follows, as to whom he shaves. And the rule is Philip shaves all persons and only those persons who do not shave themselves. So we can talk about the collection, which I called S, of all persons who are shaved by Philip. And the question is this collection a set? Well, the criteria that we have, or the criterion, the only one we have at this point, is that there needs to be a well-defined notion of membership. Membership needs to be free of contradiction. But the collection S has a problem in this regard. If Philip shaves himself, that is, if Philip belongs to the collection S, then according to his rule, he can't shave himself. His rule would forbid that. So he can't belong to S. If he belongs to S, he can't belong to S. On the other hand, if Philip does not shave himself, so he does not belong to the collection S, then according to his rule, he has to shave himself. So he has to belong to S. So we're in a bind here. If Philip belongs to S, he can't belong to S. If he doesn't belong to S, he must belong to S. So Russell's paradox tells us that membership, at least in the case of Philip, in the collection S leads to a contradiction. Either way, it's a contradiction. But if membership in S is contradictory, we can't have that membership, and so S can't be a set. So this was quite a surprise to the mathematicians of the late 19th century. And they realized that more care was going to have to be taken into what they would consider to be a set. There were also other paradoxes discovered around that period of time that are a little more mathematical. We won't go into those. So the state of mathematical thought at that time was a little bit on the edge. And for the record, I'll just give you a somewhat more formal version of Russell's paradox. Initially, it was thought that a set could be a member of itself, and at least that wasn't a forbidden idea. But I'll discuss that a little bit more later as well. So Russell considered the collection R of all sets that are not members of themselves. And in the set theory notation, it would look like this. Oh, my pen. Okay. Oops. Now, I don't know how that happened. That's a little better. Okay. Now, if we assume that R is a set, then it becomes a candidate for membership in any set, including itself. But to see the problem, all we have to do is ask ourselves, is R a member of itself? Well, if R is a member of itself, then R does not pass this membership test, and so R cannot be a member of itself. So R in R implies R not in R, a contradiction. But if R is not in R itself, then it does fit this description here in the box. It passes the membership requirement, and so R is in R. So R not in R implies R is in R. It's the same argument, but a little bit worded a little more formally. Well, so we have a contradiction, and that's Russell's paradox. Well, what to do? The shock The resulting shock from the paradoxes led mathematicians, primarily at first a man named Ernst Zermelo in around 1908, but he was joined later by a couple of other mathematicians, Abraham Frankel and Thoralf Skolem, to try to address the issue of these paradoxes. And by, let's say, 1925, they had formulated what became known as the Zermelo-Frankel axioms of set theory. Most people just say the ZF axioms of set theory. And these axioms primarily serve three purposes. The first thing is to define what it means for two sets to be equal. Speaking in more general terms in mathematics, whenever you define a new concept, one of the first things you need to do is explain carefully or define what it means for two instances of that object to be equal. And it's not quite as simple as it might sound, but it's something that has to be done. The second thing that the ZF axioms were intended to do was to postulate the existence of some sets. If you don't have any sets, you're not going anywhere. And the third thing is to provide the means for creating new sets from existing sets. So let's take a quick glance at the 9 axioms of ZF set theory. And it's kind of amazing that only 9 axioms, and there's a 10th one that we'll talk about later, were enough to jumpstart mathematics, which is a vast field of study. But this is all it took to get going. First is the axiom of extensionality, or axiom of equality. And it says that two sets are equal if and only if they have exactly the same elements. Now, just to be clear, this is not something you can prove. It's a postulate. It's an axiom. We accept this. You can think of it really as the definition of equality of sets. Axiom of the empty set. There's a set with no elements called the empty set or the null set. And it's denoted by this symbol. That is not a Greek symbol, although it resembles one. It's a circle with a line through it. It's a symbol that was inspired by the Danish and Norwegian languages, which have a similar symbol in their alphabet. And so it's just a circle with a line through it. It doesn't look too great in my word processor. It should be more of a circle, really. And again, the axiom of the empty set can't be proved. It's an axiom. We accept, we assume that there is a set called the empty set with no elements. The axiom of pairs tells us that if we have two sets, we can create a new set whose elements are exactly those two sets, no more and no less. This would be called a pair, or I think a better term is doubleton set. It's a set with two elements. If A and B are the same set, if they're equal, then the axiom of pairs gives us a singleton set, which looks like this. Next comes the axiom of union. And this axiom asserts that we can take the union of two or more sets to get another set. So we take all the elements in the individual sets and we can throw them together into one big set. Axiom of power set. If we have a set A, then there is another set. This is a well, a funny looking P is what we'll think of it. P of A, it's called the power set of A. And it's a set that consists of just the subsets of A. I haven't formally defined subset, which I'll do a little bit later, but I have a feeling you know what they are anyway. But here's an example. A is the set 1, 2. It has 4 subsets. The empty set is a subset of all sets. Then there's the singleton set 1, then the singleton set 2, and A itself. So there are 4 subsets. And that's the power set, the set containing those 4 subsets. The axiom of infinity asserts the existence of an infinite set. And the details are a little bit testy, so we won't go into that. This isn't the course in Foundations of Logic. But suffice it to say that the prototype of these infinite sets is the set of natural numbers, 0, 1, 2, 3, and so on. And I'm going to talk a little bit more about the natural numbers in a few minutes and where they come from, how they're defined. And I'm going to define infinite sets later in the course when we get to that topic. Axiom of subsets. Given a set A and some property that the elements of A may or may not possess, we can extract from A the elements that have the property and collect them into a new set. So, for example, if A is this set, and if the property in question is that the number must be greater than 0, then we can yank out those elements from A that are greater than 0 and form a new set. You know, this may seem obvious, but remember where we are. We're in the early 1900s. We've just had these contradictions that caused us to realize we can't just declare anything we want to be a set. So we are trying to develop a precise formal foundation that we hope will be contradictory free. So even if it seems obvious, we have to be very careful what we say. And we can't be sure that this isn't going to produce contradictions in the future. So far, it has not. So I think most people are pretty confident we're on safe ground. But we are still trying to be as precise as we possibly can. The axiom of replacement is a little tricky to describe, so I'm just going to give you an example. So take this set here. The axiom tells us that if we apply an operation to the elements of the set, so as an example, add 1 to the elements of A, the resulting new elements can be placed in a new set. So if you add 1 to 1, 2, and 3, you get 2, 3, and 4. The final axiom is rather difficult not only to describe but to understand. So I'm just going to leave it at this. Its most important consequence is that it forbids a set to be an element of itself, and that avoids the Russell paradox. Okay, let's talk now about the natural numbers. It might seem at first glance that the concept of the natural numbers, which start with 0, being so ubiquitous throughout mathematics, are as fundamental as the concept of set, and maybe should be incorporated initially into these undefined fundamental concepts. But in fact, that's not the case. As a matter of fact, I think if you asked most non-mathematicians what the natural numbers really are, where they came from, how they're defined, they wouldn't have a clue. But we can define them now using the ZF axioms of set theory. The number 0 is defined to be the empty set. And that exists because of the axiom of the empty set. The number 1 is defined to be the singleton set. Let's get rid of that. The singleton set containing 0. And that set is guaranteed to exist by the axiom of pairing. The number 2 is defined to be the set containing 0 and 1. And that exists because it's the union of two singleton sets. So the axiom of pairing and the axiom of union together guarantee the existence of the number 2. You can see how this is leading. Each natural number is defined using the previously defined natural numbers. So in general, the natural number n is the set of all natural numbers that came before, 0 through n minus 1. And then we can use the axiom of infinity to collect all the natural numbers into one big set, which is the set of natural numbers, and I'll denote it by this blackboard n. So now you know where the natural numbers came from. And I should make one other comment. Some of you may be thinking the natural numbers don't contain 0. I didn't even realize this until just a few years ago. But what I discovered when I first taught the transition course at UCI, I used a textbook other than my own. I hadn't written a book yet at that point. Is that many low-level math books, college algebra books, and transition books, I haven't surveyed the whole list of books. They refer to the natural numbers as starting at 1, 2, 3, 4, and so on. But if you look at a little higher level books, if you talk to mathematicians, you will find that the natural numbers start with 0. And I think you'll have to use your own judgment on this. But if you're going to do mathematics beyond the very rudimentary level, you will have to take the natural numbers as the set we're talking about here, starting with 0, starting with the empty set. I also want to make another remark on this business of mathematical intuition. We've already seen that Russell's paradox caused somewhat of a shock to mathematicians who already had decided intuitively what they should mean by a set, and they discovered that was a little too loose a concept. That's precisely why the fact that human intuition can sometimes be quite faulty is precisely why we need to put mathematics on a solid foundation, in the hopes that we avoid the kind of paradoxes that occurred in the late 19th century. Let me give you an example to illustrate how intuition can sometimes be faulty. Now, what I'm about to say, if you've already seen this before, it kind of ruins the surprise. So if as I begin this little discussion, it looks familiar to you, maybe you can try to erase your mind of what you already know and pretend you are seeing this for the first time. So consider two sets. N here is the set of natural numbers. I suppose I should have used a blackboard N here, but I didn't. E is the set of even non-negative natural numbers. Are these sets the same size, or is one bigger than the other? That's the question. Now, if you just use your intuition, if you just stare at these two sets, I think you might reasonably conclude that n is larger than e, in fact, much larger. After all, every element of E, as you see I've laid them out so that the numbers match in the two lists, every element of E is a member, an element of N. But N has a lot more elements than E does. In fact, infinitely more, the odd natural numbers. So it does seem quite reasonable intuitively to say that N is larger than E. But that intuitive argument is faulty. Our intuition here really fails us in this situation. And I'll go into precise details about why that is in a future video later on in the course. But maybe I can convince you now why that's not a good argument just by rearranging the set E a little bit. N here is the same as it was previously, but E, I now have removed these gaps. So I've written 0, 2, 4, 6, 8, 10, 12, no gaps. The list E is simply gotten from N by multiplying by 2. So 5 multiplied by 2, you get 10, 6, get 12, and so on. Now ask yourself some questions. Are these two lists comprehensive? That is to say, does every non-negative integer eventually appear in the top list? I think it's pretty clear it does. Now, this is an infinitely long list, but the point is that if you pick a particular non-negative integer, sooner or later you will be writing that integer down. Same thing for E. Every non-negative even integer appears in the bottom list. Second question, are there any duplicates in either list? And I think it's also quite clear that there are no duplicates. We never write down the same integer twice in a given list. Do we now have a pairing of the elements in the two sets? And the pairing is the element in the top list is paired with the element directly below. So I've written it this way. 0 is paired with 0, 1 with 2, 2 with 4, 3 with 6. This pairing has the property that every element from each set is used exactly once. You could call it a matching, a perfect matching. Mathematicians would call this a 1-to-1 correspondence between the two sets. Is the existence of this pairing a reasonable argument that the two lists have the same size? Well, the answer is yes. It's up to you to decide whether you believe that or not, but every mathematician does believe it, at least every mathematician who is willing to deal with infinite sets, which is pretty much every mathematician. In fact, when we come back to this topic later and look at the theory of infinite sets more carefully, this will be our definition of what it means for two sets to have the same size, if their elements can be paired in a 1-to-1 fashion. So this sort of demonstrates what you might think of as the slippery nature of infinite sets. There are a lot of surprises when we talk about infinite sets. For example, there are infinitely many different sizes of infinite sets. So we'll get to all that in the future. This subject here of one-to-one correspondences and so on is what was the beginning, really, of Cantor's great discoveries about infinite sets in the late 1800s. Unfortunately, Cantor was quite conflicted by his own discoveries, and it led him to have, among other things, to have cycles of manic depression. He was hospitalized for them. He had a real tough time with his own discoveries, rationalizing them. And that was also partly due to severe criticism that he received from some mathematicians, some highly regarded mathematicians, some philosophers, and some theologians who felt that somehow all this discussion was an affront to God. So I'll touch upon that a little bit more later when we talk about the mathematics of infinite sets. So let's take a look at some of the sets that will be of concern to us in the course on discrete mathematics. First, let's look at some sets of numbers. The natural numbers that start at 1, natural numbers without 0, are generally referred to as the counting numbers. After all, when you count, you start with 1. You don't start with 0. Although we may do that a few times in the future, because sometimes it actually is useful to start with 0. And then we have the natural numbers. The integers are the natural numbers together with their negatives. And we could, at this point, give a formal definition of integers, but that takes us again away from discrete math. I've already probably done too much of that in some people's opinion. So I won't formally define the integers. This is a set we will have much use for at various times in the course, so I wanted to give it some notation. Z sub n is the set of integers between 1 and n. The rational numbers, as you probably know, are the numbers that can be written in the form p over q, where p and q are integers and q is not 0. That's a very informal way of defining the rational numbers, and there is a more formal way using ordered pairs and equivalence relations, which will be a topic we will cover in the future. Rational numbers also are the numbers that can be written as repeating decimals. It can be shown that the numbers pi and square root of 2, among others, of course, are not rational. So they can't be expressed in this form p over q. They can be expressed as non-repeating decimals, but not as repeating decimals. Actually, it's quite easy to show that the square root of 2 is not rational, and we're going to do that when we talk about proof techniques later in the course. But it turns out to be very difficult to prove that pi is not rational. And there are a number of proofs of this fact. And just so you are convinced of this, I wrote down some names. There's Lambert's proof, there's Hermite's proof, Cartwright's proof, Niven's proof, and so on. And so this kind of testifies to the fact that there's no simple proof. If there was, we'd know it and we wouldn't need all these others. And these proofs are beyond the scope of this book, so I won't go into that. We also can't give a formal definition of the real numbers, because that actually is fairly complicated. There's a couple of different versions that come out the same. And this properly belongs to a course in what is called real analysis. And it's an advanced undergraduate topic, really. But suffice it to say something you probably already know, and that is there's a real number for every point on what is called the real line. The irrational numbers are the real numbers that are not rational. So pi and the square root of 2, for example. This set here has quite a fascinating history. It's the set of all n such that n is an integer greater than 2, and there exist positive integers x, y, and z for which this equation holds. As you probably know, there are many positive integers x, y, and z for which this equation holds. This is the equation from the Pythagorean theorem. For example, 3, 4, and 5 fit this equation. And for that reason, this ordered triple is called a Pythagorean triple, because it fits the Pythagorean theorem. Well, this led mathematicians to wonder whether there were solutions to the same equation, but with exponents larger than 2. So, for example, here n would be 3. A brilliant mathematician named Pierre de Fermat, who was one of the founders of modern probability theory and lived from 1601 to 1665, he was the first to give this question serious thought, at least as far as I know. And in fact, he claimed to be able to show that there were no exponents, that there were no positive integer solutions for exponents greater than 2, including this one, just the cubes. And Fermat wrote in the margin of one of his books, quote, "To divide a cube into 2 cubes," which is what the phrase he used for solution for this equation, "a 4th power into 2 4th powers, or in general any power whatever, into 2 powers of the same denomination above the second is impossible. And I have assuredly found an admirable proof of this, but the margin is too narrow to contain it." Okay. So this set S, he claims, is empty. As long as here n is greater than 2, this is the empty set. Well, this became known as Fermat's last theorem, that this set was empty. And it's really unfortunate that he didn't take the time to write his proof down somewhere else. He must have had paper and pencil or quill or whatever it was they used, because it took 350 years before mathematicians were able to show that Fermat was right, that set S is empty. 350 years. So I guess one has to suspect that Fermat's intuition failed him in this case, and that his proof was faulty. Well, I think that should do it for this video. Thank you for watching, and I hope to see you in the next video.